the time has come for us to start a class. My dear students, my name is Benatang Paton, and I welcome you to the channel Classroom, where we learn together. I assume you're all doing well. So once again, I thank you all for tuning in. And today, my dear students, the topic that we will be discussing in detail, will be magnetic field on a straight wire or magnetic field in a current carrying straight conductor. So this is what we will study today. This is a very easy topic, and for this you need to be thorough with Maxwell's right-hand thumb rule, which we have discussed in the previous video, which states that if the thumb points in the direction of current, then the direction of the curl of the four fingers will give you the direction of magnetic field. So this is going to be very, very important in today's topic. So without wasting any time, let us jump into the topic and learn. So in today's class, in the first part of the video, we will be learning about magnetic field on a straight current carrying wire. So the wire will be straight, the current carrying wire will be straight, and we will be studying the nature of the magnetic field on a straight current carrying wire. That is what we will be learning in the first half of the video. So my dear students, grab a notebook, grab a pen or a pencil, and make sure that you take down the notes, because these notes are going to be very much helpful for you. So let's start. So first of all, imagine that there is a cardboard here. So let us draw a cardboard. Not like this. Let me draw a little slanting. Let it be a little bit of a parallelogram. Let's say that this is the cardboard. So let's say this is the cardboard. Now, in this cardboard, let's make a hole, and then let us pass the straight current carrying wire through this hole. So let this be the straight current carrying wire. Now, indicate the direction of current. Let's say the current is going upwards. So this is the direction of current. So let this be the direction of current. Now, what we will do, we will apply Fleming, or why do I always keep saying Fleming's? Fleming's left hand rule is, we have not even started. It will come in the next topic. So I will be using Maxwell's right hand thumb rule. So time to use Maxwell's right hand thumb rule. So this is the straight current carrying conductor. You know the rule, which is the thumb should point in the direction of current. So the current is going upwards, is it not? So is this the right orientation, my dear students? Is this the right orientation? Is my thumb pointing in the right orientation? Yes. So the thumb is pointing up because current is going up. So according to the rule, the thumb should point in the direction of current. So the current is going up, so the thumb should point up. Then in this way, the direction of curl of my four fingers. So these four fingers, 1, 2, 3, 4, the direction of curl will give the magnetic field. So the curl will be circular, isn't it? So the magnetic field will be circular. Alright, it will be circular. So the curl, the drive is circular, so it will be circular. But then we will also require the direction. Now this is the tricky part. Now the magnetic field on a straight wire will be circular. It will be concentric circles. Remember, these are all circular. These are all concentric circles. These are concentric circles. What do you mean by concentric circles? Concentric circles, my dear students, are circles which share a common point. So the common point here is this. This point is the common point. And all these circles are sharing this common point. This common center. Sorry, not point, but common center. So circles which share common center are called concentric circles, and all of these circles are sharing this common center. So these are called concentric circles. Circles which share common center. So these circles are all concentric. Now time to find the direction of magnetic field. So in order to find the direction of magnetic field, now the direction of magnetic field here will be either clockwise or anti-clockwise. Now there are some of you who are confused with this term called clockwise or anti-clockwise, for which let me help you. In today's video, let me clarify this clockwise anti-clockwise dilemma. So I want all of you to learn how to find direction, which will be called clockwise, what is clockwise direction, which is anti-clockwise direction, for which you need to know this. Okay, this is a watch. Okay, this is how our watches are designed. Now you know that if this is the second hand, okay, means if this is the minute hand or the seconds hand, okay, you know that if it moves like this, okay, if it moves in this direction, this is called clockwise. Yes or no? This is how the hands of the clock move, is it not? Okay, this is clockwise. Okay, this is called clockwise. Now then what about this? If the hands of the clock, they move like this, then what will this be called? This is what we call anti-clockwise. Okay, this is what we call anti-clockwise movement. Now let's start from here. Okay, now the starting point is here at 3. Okay, at 3. Now if I move like this, then my dear students, tell me, what is this movement? Am I moving clockwise or anti-clockwise? This is a clockwise direction, is it not? Okay, so this is a clockwise direction. Now what if I start from here again and then I move like this? I move like this. Then this is clockwise or anti-clockwise? This is anti-clockwise, or how I like to tell my students, 3 to 12, 12 to 9, 9 to 6. Okay, so if you are moving, okay, if you are moving like this, remember, you have to remember from where you are starting. Let's say I start from here and I'm moving like this. That means the movement is from 6 to 3 to 12. So this is anti-clockwise. Or let's say I start from here. Okay, I start from here, which is 9, isn't it? And then I go like this, 9 to 6, 6 to 3, 3 to 12. This is again anti-clockwise. Let's say I start from here. Okay, I start from here. Okay, and then I move like this, 9 to 12, 12 to 3, 12 to 3 to 6. What movement is this? In which direction am I moving? Is this clockwise or anti-clockwise? This is clockwise. Again, let me show you. What if I start from here? Okay, what if I start from here, 6, and then I go to 9, 6 to 9 to 12 to 3. This is clockwise or anti-clockwise? This is clockwise. So I hope it is clear. Okay, to know whether it's clockwise or anti-clockwise, always know the starting point. So if I keep it like this, okay, and I move like this, 3 to 12, this is anti-clockwise. Let's say I start from here. Okay, I start from here and I'm moving like this. Then this is clockwise or anti-clockwise? This is clockwise. Okay, I'm moving 6 to 9 to 12 to 3. This is how a normal clock moves. Okay, so this is what clockwise and anti-clockwise is. Okay, so remember this, because this is going to be very much useful. Now apply Fleming's left hand rule. Now see, this is my hands. Okay, now I'm going like this. Okay, I'm going like this. So I'm going like this. So I'm going like this. Let me show you. So I'm going like this. Okay, I'm going like this. Let me keep it like this. Okay, let me keep it not straight, like this, like this. Now you tell me. So my drive is like this. My drive is like this. Let's see. Right now I can say that the position of my finger is 3. Then I'm going like this. So from 3 to 12. Nah, see, from I'm starting like this. No, I'm curling like this. So from 3 to 12. See, 3 to 12, 3 to 12. I'm starting from 3 and I'm going to 12. 3 to 12. This is clockwise or anti-clockwise? This is anti-clockwise. So here, at this very point, from where I'm using Fleming's left hand rule, here, this drive, this drive, this is anti-clockwise. This is anti-clockwise. Here, the magnetic field is moving anti-clockwise. Okay, then after this, it's very easy. You just follow this. Okay, you just follow this, and then the arrow will change. So the particle is moving like this, and again it will come down here. So here the arrow will be reversed. Then it's going up. Then again it will come down. Then it's going up. Then the same arrow will be like this. So this is how you find the direction of magnetic field on a straight current carrying wire. Easy, very easy, nah? Let's do one more. So now we'll do the next one. So remember here, my dear students, that magnetic field, okay, magnetic field here is anti-clockwise, okay, because it's going like this from 3. You know, here is 3, this is 12, this is 3. Remember, every time class, this is 3, this is 12, this is 9, and this is 6. Okay, so in front of you is 6, this is 3, this is 12, and this is 9. Okay, so remember, I started like this. It's going like this. So 3 to 12. Okay, so it is anti-clockwise. Now let's go to the next one. Let's change the direction of current. So again, okay, let me utilize this area because I want to write there the characteristics afterwards. So let me save some space there. Again, the same thing. Okay, let's take the center and let's say this is the current carrying wire, and this time let's reverse the direction of current. So now the current is flowing downwards. Let the current flow downwards. Okay, then this is the cardboard, same again. Okay, now apply Fleming's left hand rule here. So not every time Fleming's left hand rule, sorry, Maxwell's right hand rule. Okay, apply Maxwell's right hand rule. Okay, I don't know why I keep on saying Fleming. It should be Maxwell's right hand rule. So apply Maxwell thumb rule. Okay, so current is going down, so my thumb should also go down. So this is the right orientation. Okay, so let's orient it. So the thumb is going down, the thumb should point in the direction of current. Right now the current is going towards the floor, so my thumb is pointing down. Okay, and then now look at the drive. Okay, so you know that the curl of my fingers will give the magnetic field, so it will be circular, no doubt. It will be circular. Okay, the tricky part here is, okay, to indicate the direction. But let me give you a hint here. Okay, on reversing the current, the direction of magnetic field changes. I repeat, on reversing the direction of current, the direction of magnetic field will also change. Okay, so basically what I'm telling you is, since here it is anti-clockwise, here it will be clockwise. Why? Because the direction of current has changed. Current was previously going towards the ceiling, towards the roof. Okay, now current is going down, so direction of current has changed, so the direction of magnetic field will also change. So magnetic field here will be clockwise, but let's find it ourselves. Okay, let's find it ourselves. Okay, we will not memorize, we will find it ourselves. We will understand it and find it ourselves. So let's use thumb rule here and let's find it. So remember now, so I told you now this is 3, facing you is 9, facing you is 6, this is 9, and this is 12. Okay, the whiteboard is 12, this is 3, this is 6, facing you is 6, and this is 9. So now you see the curl of my fingers is gonna drive like this. It's gonna drive like this. So from 3 to 6 now. If from 3 to 6, then clockwise or anti-clockwise? It's clockwise or anti-clockwise? It is clockwise. So it's going like this. So it's gonna come out from this end. Okay, so it's coming like this. The thumb is pointing down, so it's gonna come out like this. It's gonna come out like this. So it's coming like this. So it will be clockwise. So it will be like this, like this, like this, because the curl is like this. Now see, from 3 to 6 now, 3 to 6. See, 3 to 6. Okay, it's coming like this, and then it will go here, it will go here, it will go here. See, opposite now. Here they were going like this. They were going like this, which is anti-clockwise. Here they're coming like this. Here this is 3 to 12. This is 3 to 6. If movement is from 3 to 12, it is anti-clockwise. If movement is from 3 to 6, it is clockwise. After all, after 3 comes 6, then 9, 10, 12. Okay, so the direction of magnetic field is clockwise. Okay, so magnetic field is equal to clockwise direction. Okay, clockwise direction. This is anti-clockwise direction, this is clockwise direction. I hope you all understood. Okay, now let's write down the points what we have just discussed. Let's write down in points so that you will be able to remember them in detail. Okay, so let's write down the points. So properties or points, let's just write points. Okay, points to remember. So these are going to be very important. Whatever we have just discussed will be written point wise from, okay, point wise. So let's write point number 1. Let's save space. Okay, so magnetic field lines. magnetic field lines are concentric circles. Concentric circles. They are concentric circles. Yes or no? Are they concentric circles or not? Yes, they are all concentric circles. Okay. Point number two. Point number two. Direction of magnetic field lines. Direction of magnetic field lines. There goes my alarm clock. You know what is the time now? The time is 12:45. Okay, this class is being recorded at 12:45 early in the morning. So direction of magnetic field lines reverses as we reverse the direction of current. The reason why I record at this hour is because it is quiet. Okay, it is quiet. So I like this quietness. If only I could teach like this in my classroom. But the story in my actual classroom is very different. Okay, it's just fish market. So I always tell my students to give me this environment, but then it's impossible to get that in my actual classroom. Okay, but if my students are watching, this is what I want from you all. Okay, and at the same time I will tell you, my dear students, to give this kind of environment to your teachers so that your teacher can teach you effectively. Okay. Number three. So direction of magnetic field lines reverses as we reverse the direction of current. So see here, the direction of magnetic field line here, when the current is going upwards, is anti-clockwise. On changing the direction of current, the direction of magnetic field line has changed. It goes clockwise. Okay, so very important point. Okay, then when current flows upwards, direction of magnetic field lines, is, when current flows upwards, direction of magnetic field lines is anti-clockwise. Point number four. When current flows downwards now. When current flows downwards, direction of magnetic field lines is when current flows downwards, my dear students, look, when current flows downwards, direction of magnetic field lines is clockwise. Then point number 5, which is a very important point. Okay, let's put a star mark here because this has been asked in exam. So you have to be ready. Okay, you have to be ready for this, for your board exam. So point number 5 is magnetic field produced is directly proportional to current, flow and inversely proportional to distance. from the conductor. So let us spend some time here to understand what it means. So let me erase this. I suppose you have all drawn this picture. Now, this fifth point, what does it mean? The fifth point says magnetic field produced is directly proportional to current flow and inversely proportional to the distance from the conductor. So let's understand this one. So let us take this. So let us say current I is flowing here, okay, and then let us keep the magnetic compass here. Now this is the direction of pointing of the magnetic compass towards the north, so it's pointing towards the yes, it's pointing towards the north. Now yes, now what will happen? Current is flowing here, so it produces magnetic field, so it will interact with this magnetic compass, and then what will happen? Deflection will be noticed, so we'll see a deflection. So let's keep the deflection, let's say like this. So let's say this is the deflection. So this is the deflection, this is the original direction. Check out the amount of deflection, which is theta, okay. Now this is the distance here, then let's increase the distance. Let's bring it here now and let's check. So the needle is now here, it's pointing towards the north, okay. Now here, how will the deflection be? The statement says that, okay, it is inversely proportional to the distance from the conductor. That means the further it is from the current carrying wire, the deflection will be less. Why? Because the magnetic field will be less, isn't it? Here, so here the magnetic field reaching here is less. So if the magnetic field reaching here is less because of the distance, then the deflection will be more or less. The deflection will be less. So here the deflection will be very less, so the needle will go like this. So you can see this is the original direction and this is the deflected. Check out the theta. This is theta, okay. This is theta. Angle. This is angle only, okay. So this is the angle of deflection. This is the angle of deflection. You can see which one. Where is the deflection more? A or B? Deflection is more at A. Reason? Because it is very close to the current carrying conductor, okay. The closer you are to the current carrying conductor, the more magnetic field, okay, you will experience. That means the deflection will be more, because it's experiencing more magnetic field, deflection is more. And the further you are, the magnetic field decreases with distance, thereby the deflection will be less. So this is what the fifth point is, okay. Now we'll discuss the next point, which is magnetic field produced is directly proportional to current flow. For the next one, let us do one thing. Now let's increase the current. So let's say 2I. Previously only I was flowing, okay. Now 2I is flowing, okay. So 2I is flowing. That means double the current is flowing, okay. Double the current is flowing. And now let's see. So let's keep the same distance here, okay. So let us draw the needle somewhere here, and then this is the original direction in which the needle is pointing, which is north. Now what will happen? The deflection will be like this time, okay. So now you tell me. Check out the angle of deflection, theta. Which is more, this or this? Which is more, this one or this one? Let's say this is C. So A is more or C is more? The amount of deflection in A is more or C is more? Undoubtedly, the amount of deflection in C is more. You know why? Because I've increased the amount of current. If the current flow is more, then the magnetic field produced is also more. Remember this. That means magnetic field is directly proportional to current, and magnetic field is inversely proportional to distance, okay. So the magnetic field is inversely proportional to distance, and magnetic field is directly proportional to the amount of current flowing through the wire, which means more current flowing in the wire, the deflection will be more, which is visibly seen here in the figure. Okay, and then the closer, okay, the closer the needle, the more the magnetic field it will experience. The further, the more the distance, the far away the needle, the lesser the magnetic field it will experience. How do we know that? By the deflection which is observed in the needle. If it is near, the deflection is quite big. If it is far, because the magnetic field interacting is less, so deflection is less. Okay, all right. So this is everything about magnetic field on a straight wire. I hope you all understood. Okay, now let me erase this, and then let me we'll discuss the second topic, which is magnetic field on a current carrying loop. Now, my dear students, we will be discussing the next topic, which is magnetic field due to circular loop. So now here the wire will be bent in the form of a loop. Now if you ask me what is a loop is a wire which is bent in the form of a circle. Okay, a circle is also called a loop. So the wire will be bent in the form of a circle. Okay, now every wire has got two ends, the starting and the bottom. So let us show that. So we can make it like this. Okay, one end, the other end, current will enter from one end, travel all the way, and then exit from the other end. So this is what a loop is. And then we are going to study the magnetic field in a current carrying loop. Okay, so to start the discussion, let us assume a cardboard again, and then now we'll be making two holes. Let's make it somewhere here, and let's put it somewhere here. And then this is the wire, and then okay, the wire will be like this. So current is entering from this end. This is current I, and current is going like this. Then current will travel all the way like this, and it will exit from this end. Yes or no? Okay, now what we will do is, let this be point number 1 and let this be point number 2. Now apply right hand thumb rule on point number 1. So apply right hand thumb rule on point number 1. So to apply right hand thumb rule, you need to know the direction of current. Do you know the direction of current on point number 1? The current is going upwards, isn't it? See, the current is going upwards, current is going upwards, current is going upwards. So right hand thumb rule, the thumb is to point in the direction of current. So this is the right orientation. Okay, the thumb is along the direction of current. The current is going towards the ceiling. Okay, at this point, okay, at this point, the current is going upwards like this. So my thumb should point upwards. Then the four fingers will curl, which will give me the magnetic field. So the magnetic field will be circular. Yes or no? Yes. Okay, so very easy. Okay, we are familiar with this. Then now tell me the direction of the magnetic field. Will it be in clockwise or anti-clockwise? For this, again, apply the right hand thumb rule. So I only told you this is 3, I am 9, this is the marker, this side towards you is 6, and this one 12. So we'll start from here. So it's going like this. So 3 to 12, 3 to 12, 3 to 12, 3 to 12 is what? Clockwise or anti-clockwise? This is anti-clockwise. So the direction of magnetic field is anti-clockwise. It goes like this, drives away. It goes like this, drives out. It goes like this, drives out. Clear? Very easy, nah? Okay. So done here. Now let's go to point 2. Again, point 2. In point 2, current is going downwards. So current is going downwards. So right hand thumb rule. Thumb should point down. Yes or no? Thumb should point down. So thumb is pointing down. Then now look here. This is 3. This is me is 9. This is 12. This side is 6. So now we are starting like this. Okay, we are starting like this. See. So we are going to go like this. Thumb is going down, but then the curl will be like this. So from 3 to 6. It's from 3 to 6. From here, this is 3 to 6. So 3 to 6. The direction of curl is 3 to 6. 3 to 6 is what? 3 to 6 is clockwise or anti-clockwise? This is clockwise. Okay, clockwise. So here it will be clockwise. So this is these are the magnetic field, and then it will be clockwise. So it's moving like this. It's clockwise, and it will enter here. All right, so this is how you find the direction of magnetic field in a current carrying loop. Okay, now I want to know, okay, I want to know what is the direction of magnetic field in the middle. I want to know what is the direction of magnetic field in the middle. So let's find out the direction of magnetic field in the middle. So this is the loop that we are drawing, okay, which we have drawn. Let me now draw this one, okay, and this is point 1 and this is point 2. Okay, I'm drawing point 1 and point 2, point 1, point 2. In point 1 here the magnetic fields are like this, okay, round, okay, then this goes bigger, this goes bigger, this goes bigger. Similarly here also it goes bigger, it goes bigger, they only get bigger, they only get bigger, they only get bigger. Now like this you can see, okay, you can see at the corners they are round, but as it goes, okay, further away from the corner, what happened? It's the circles are opening up, the circles are opening up, the circles are opening up. If we continue this, then can you tell me what will be, how will the magnetic field be in the exact center? How will the magnetic field be in the exact center? Can it be a straight line? Yes, my dear students, can it be a straight line? Can it be a straight line in the middle? Yes, in the middle it will be a straight line. Okay, so remember, okay, at the corners, at this point, point 1 and point 2, at point 1 and point 2, okay, they are circles, okay, they are round, but then, okay, as we move closer and closer, as we approach the center, the circles, they open up, they open up, they open up, and then finally, okay, at the exact center, the magnetic field is a straight line. So the magnetic field is a straight line, but we are not done. Now the magnetic field is a straight line, but then I need to know the direction of this magnetic field. I need to know the direction of this magnetic field. Will it be like this, or will it be like this? Which one will it be? Which one will it be? Will it be this one, or will it be this one? So how do I find out? How do I find out? How do I decide? In order to decide, look at this, see here, okay, here you see the magnetic field, okay, the magnetic field lines are driving in, isn't it? They are driving in, see, they are driving in, isn't it? From here, look at the direction of arrow, they are coming out like this, and then they're driving inside, so they are going inside, okay, they are going inside, so the magnetic field direction will be like this. So the correct magnetic field direction is like this. How like this? Because look at this, see, they are going like this, they are going like this, so the magnetic field will be going inwards, okay, so this is going inwards, this one is inwards, okay, it's going inwards. I hope it's clear, okay. Remember this. Even here also, if you look at this one, if you look at this, okay, they are going inside the loop, isn't it? They are going inside the loop, see, they are going inside the loop, they are going inside the loop, and here also they are going inside the loop, so they are going inside the loop. The loop means this one, okay, or for example, let me show you this one. So this is the loop, so this is the loop, so point 1 is here, point 2 is here, okay, so point 1 and point 2, so in point 1 is going inside, in point 2 also is going inside, so point 1 going inside, point 2 also going inside, okay, so point 2 also going like this, see, point 2 going inside, point 1 going inside, so the straight one will also go inside. I hope it's clear, okay. Now, so that is done. Now again, let's continue with our discussion. So let me erase this now. I hope you are all following. Next, consider this loop again. Consider two loops. Now here current is flowing in this direction, and here current will flow in the opposite direction. That means current will flow this, and it will come like this. So two loops in which the direction of current are opposite, okay. So current here, this is clockwise or anti-clockwise? Tell me. Current is flowing clockwise or anti-clockwise? Anybody who can tell me? Tell me the direction of current here. Is this clockwise or anti-clockwise? Pause the video and tell me whether this is clockwise or anti-clockwise. What did you write? Clockwise or anti-clockwise? This is, now see, this is clockwise. How is it clockwise? See here, it's going like this, isn't it? So it's going like this. See, this is 9 o'clock, this is 12 o'clock, this is 3 o'clock, this is 6. So 9 to 12 to 3 to 6. So this motion is called clockwise. So current is going clockwise. So current is clockwise. Then here current is anti-clockwise. So this is anti-clockwise. You can check and see, is it anti-clockwise? Yes. Let's start from here. I told you now, always select one direction. So let's start from here. So it's going like this. So 9 to 6 to 3 to 12. So this drive is here. So we are starting from here. Always remember your starting point. You are driving like this. This is anti-clockwise. Always remember your starting point. You are driving like this. This is called clockwise. You are driving like this. This is anti-clockwise. Understood? Now, what we are going to do? What we are going to do is apply apply thumb hand rule, and then you will get the magnetic field here. Okay, then apply thumb rule here and get the magnetic field here. Okay, so if you apply thumb rule here, the magnetic field will go inside like this, and then they will exit like this. If you apply thumb hand rule here, okay, then they will appear to be coming out from here, and then they will enter here, they will enter here. Now, so magnetic field, I want to know the nature of the magnetic field. Okay, listen to this question, my dear students, and answer me this question. The question is, I want to know the nature of the magnetic field. Means I want to know whether the magnetic fields are going inwards or coming outwards. Can you tell me whether the magnetic field here in this loop are going inwards or they are coming outwards? Okay, so are they going inwards or are they coming outwards? Better with this one, nah? Okay, so the magnetic field here, okay, for this loop, the magnetic field here are going inwards or are they coming outwards? Which is correct? They are going inwards, isn't it? They are going inwards. See, look at this one. This one is this one. The magnetic field is going inwards. Okay, so here at this end, 1 is going inwards. Then what about 2? At 2 also, look here, it's going, look at this arrow, it's going inside, isn't it? So here also is going inside. See, at 2 also is going inside. At 2 also is going inside. So the magnetic field here on this loop, okay, from your perspective, okay, it's going inwards. This is the magnetic field lines are going inwards. Even here also the magnetic field lines are going inwards. So this is inwards. So the magnetic field lines are going inwards. Okay, then let's go here. Then we are finding the magnetic field here also here. Okay, then here also we are finding. Now, so if we apply right hand thumb rule here, then the magnetic field are going down. So the current is going down, sorry, the current is going down. So it will be like this. So the drive will be, it will be coming out. So it's coming out, it's coming out, it's coming out, it's coming out. Then again, it'll go in, it'll go in. Then here, if we apply thumb hand rule, the current is going up. So the drive is like this from 3 to 12, which is anti-clockwise. So the drive is like this. Then they will come out. Now, the question is same. The same thing I'm going to ask you, because you have to tell me the direction of magnetic field. So tell me the direction of magnetic field. I want to know the nature of magnetic field in this loop, okay, where the current is flowing anti-clockwise. When the current is flowing clockwise, the magnetic field is inwards. When the current is flowing anti-clockwise, okay, it will be outwards. But let's check, okay, now this is 1, this is 2. Now look at this one. Look at the magnetic field here. So here, if you look at the magnetic field here, see, look at this arrow. Look at this arrow from this point. So don't they appear to be coming out like this? See, look at this arrow. Okay, this one. Okay, this side is here. Don't consider this one. Consider this one. We are talking about inside. Okay, inside the loop. We are talking about this region. That means we are talking about this region. Okay, we are talking about this region. So focus on this and this. We'll focus on this. So don't focus on this one. Don't focus on this one. Focus on this one and focus on this one. Let's first focus on this one. So if you look, the arrows are coming like this. Now see, they appear to be coming out now like this. See, is it not? Do they appear to be coming out or not? Yes, they appear to be coming out. Then if on one side they're coming out, then even here also they'll be coming out. Understood? Same here. On one end they were entering now, then even this side also they will enter. Okay, this is a hint given. I'm giving you a hint. Remember this. If on one end they are entering, if at one they are entering, then even at two they will be entering. So here, if at one they are coming out, then even at two they'll come out. Let's confirm. At two, are they coming out? Are they coming out? See, look at these arrows. Are they not coming out? They are coming out of the loop, isn't it? They are coming out of the loop. They are coming out of the loop at one. They are also coming out of the loop at two. So they are coming out. Coming out means, see, this is outward. This is inward. This is outward. Coming outwards. Okay, out of the loop, going in the loop, out of the loop, in the loop. So this time it is out of the loop. Okay, so this time it is out of the loop. So magnetic field is outwards. All right. Now I want you to let's consider a bar magnet now. So you know a bar magnet. You are familiar with a bar magnet. In a bar magnet, we have two poles, the north and the south. And you know very well by now that the magnetic field lines, they emerge from the north. They emerge from the north, and then they travel all the way, and then they enter from the southern end, isn't it? This is how the magnetic field in a bar magnet is. Now imagine that this marker is a bar magnet, and let's say this black one is the north. Okay, now if I hold it like this, now this is the north and this is the south. So magnetic field lines, they are emerging from which end? From the northern end or from the southern end? They are emerging from the northern end. So magnetic field lines are coming out of the northern end, and then they are entering inside the southern end. Yes or no? They are coming out from this end, and then they are entering inside the southern end. They are coming out from this end, and they will take a closed curve and enter inside the and enter from the southern end. Okay. Now remember, what if I make the north face towards you? What if I make the north face towards you? Then how will the magnetic field look? How will they appear to move from your perspective? They will appear to come out, isn't it? They will appear to come out from you and enter from here. Okay, the south is on my end, the north is facing you. So how will the magnetic field lines appear from your end? They'll appear like they're coming out from you. Okay, they're coming out. See, they'll come out like this. They're coming out towards you. Okay, they'll come towards you and enter from this end. They'll come towards you. So they're coming out. Okay, the magnetic field lines, they're coming out from this end. Okay, now what if I show the south towards you? Then here, how will the magnetic field lines appear to move? They are coming out from the north. So the magnetic field line, my finger is the magnetic field line, and then it's entering inside the south. Then from here also one magnetic field line, and they're entering inside the south. Then again from here one magnetic field line, and they're entering inside the south. So from your end, they'll appear to be going in. Okay, they'll appear to be going inwards. They appear to be going inwards. Whereas from the south, they appear to be from the north, they appear to be coming outwards. Yes or no? From the north, they'll appear to be coming outwards. Okay, and then they'll go inside the south. So from the south, from the magnetic fields which have come from the north, they'll appear to go inside. They'll appear to go inside from this southern end, and from here they appear to be coming out. So from the northern end, they appear to be coming out, and from the southern end, they appear to be going inwards. Yes or no? So southern, on the south, magnetic field lines are entering. From the north, they are coming out. So outward. from the north outward, from the south inward, from the south inward, from the north outward, from the south inward. So inward means south, so this becomes south, this becomes south, and outwards this is north, so this becomes north. Clear or not? Okay, this is a very important point. Okay, so this becomes the south pole and this becomes the north pole. I hope it's clear. Okay, so how are we able to determine? So we are saying that this is the south pole and we are saying that this is the north pole. So how are we able to determine, okay, whether a loop is south pole or north pole? Remember this: magnetic field lines in a bar magnet, they emerge from the north and they enter through the south. So this is the north, this is the south. So they emerge from here, they come out from here, and they enter through the south. So if I bring it towards you, the north pole, the magnetic field lines are traveling outward, they're coming out. And if I show you the south, they're entering through the south. So entering inside south. Inwards, magnetic field lines going inwards, south pole. Magnetic field lines coming out outwards, north pole. Okay, so this is how we can determine the south and north of a loop. Okay, just by studying the nature of the magnetic field. Okay, so if the magnetic field lines are going inwards, okay, it means this part is south pole. If the magnetic field lines are going, okay, if the magnetic field lines are coming outwards, that means this end is the which pole? North pole. I hope it is clear. All right, so remember this one. So now you tell me, what pole is this one? What pole is this one? What pole is this one? Look at the magnetic field lines. Are they going inwards or are they coming outwards? Correct, they are going inwards. That means what pole is this one? This is south pole. Understood? This is how easy it is. Understood? Why is it south pole? Because the magnetic field lines are going inwards, isn't it? Okay, the magnetic field lines are going inwards, so south pole. The magnetic field lines going inwards, south pole. The magnetic field lines are coming outwards, they're coming out, so north pole. Going in, south pole. Okay, so remember this: when the current is clockwise, magnetic field will go inwards and the pole is south pole. When the current is anti-clockwise, the magnetic field will come outwards and the pole is north pole. All right, now we will erase this and we'll write down the points, okay, one by one. So I have to make space for the points to write. Whatever we have discussed, we'll write down. So points, let's write down the points. Point number 1, magnetic field around a circular loop is also circular. What is the meaning of this one? It means this one, which I already erased it, but I'll show you. So this one, so this one we are talking about this one. Okay, this part, these are circular. Okay, point number 2, at the center, the magnetic field lines are parallel. So you know that here at the center it is a straight line, isn't it? Okay, so we are talking about this. So here it will be parallel. Remember this. So here they are all becoming bigger and bigger. Here it's circle, here it is round, but then it only gets bigger and bigger, isn't it? So finally, okay, at the center it will become straight parallel lines. Okay, so at the center the magnetic field lines are parallel. Point number 2 done. Point number 3, the part from where the magnetic field lines entering the coil facing us is south pole and the other is north pole. Meaning, so here the magnetic field lines will appear to be entering. So they will appear to be entering. So the magnetic field lines will appear to be entering. So this part is the south pole, okay, and the other one will be the north pole. Remember, so the magnetic field lines are entering here. So this part, the part facing you, okay, this part, this becomes the south pole. But what about the other? Because this wire has got backside also. Let me show you the backside. This part, this part. What about this part? So from here, if I do like this part which is facing you, this part, okay, where I have made 1 and 2, where the marker has left its mark, this part, you are seeing this face, but for me, I am seeing the backside. So this part of the wire which is facing you, this one here, okay, here the magnetic field lines, they are entering, but from my end, let me show you, okay, from my end, okay, it will appear to be like this. So from my end, the magnetic field lines are coming out, but from your end, they're entering, but from my end, they're exiting, they're coming outwards. From your end, they're entering, okay. So the part from where it appears to be entering, it is south pole, and then from my end, where it appears to be coming out, it is north pole. So this part is south pole and this part is north pole, remember, okay, and the other is north pole. Number 4, current clockwise. If current is clockwise, then which pole is it? If current is clockwise, this is current going clockwise, this is south pole. Point number 5, if current is anti-clockwise, then it will be opposite, okay. Whenever we change the direction of current, the direction of magnetic field changes. So if current is anti-clockwise, then it will be north pole. Point number 6, now magnetic field produced is directly proportional to current and inversely proportional to the distance from the conductor. These points are very, very important. You have heard the explanation, but this is your notes. If you study this, it will make it stay in your memory for long, okay. This will develop a map inside your head with which you will understand better, okay. So the 6th point, very important, okay. So what does it mean? So magnetic field produced is directly proportional to current and inversely proportional to the distance from the conductor. Now let me explain to you. So now let's take this circle again. At the same time, let's make another circle, okay. One is a big circle, the other is a smaller circle. Big circle from the center, radius capital R. Small circle from the center, small r, okay. Now remember, let's keep the current same, okay. Current would same, current is I, okay. So current I is traveling, same current, okay. Remember, same current. same current is traveling, same amount of current is traveling. Okay, now what will happen? Magnetic field will be produced. So we know magnetic field will be produced. Let's first start from here. So at the center, at the very top, it will be like this. Then again it will become, then again here also, this is the nature of the magnetic field. Then here also, then here also. Now the question is, which among, let's say this is A and let's say this is B. So which one will have greater magnetic field, A or B? What is your answer? Class, tell me which is your answer. A will have stronger magnetic field or B will have stronger magnetic field? Here I'm talking about this point. Okay, if at this point, who will experience more magnetic field? This point, at this point, at the center. Okay, if you are here at the center, this point will experience more magnetic field or this point will experience more magnetic field? The magnetic field experienced by this point, okay, or this point, which point will be more? Okay, let's say this is point P and let's say this is point Q. So point P will experience a stronger magnetic field or point Q will experience a stronger magnetic field? The answer is point P. Why? Why point P? Because check out the magnetic field. The magnetic field are more denser. They are more close to each other and they are more dense. So denser magnetic field will give you, okay, the denser magnetic field will produce more. Okay, if the magnetic fields are closer, then they produce a stronger magnetic field. But look at here. Okay, look at here. The magnetic field are spaced apart. They are widely spaced apart. Therefore, the strength of the magnetic field here is weak. Okay, so if the distance between the magnetic fields are large, then the magnetic field around it is weak. If the magnetic fields are closely packed, then you experience stronger magnetic field. So this will have stronger magnetic field. So magnetic field of A or say is greater. Okay, the reason is due to denseness or closeness of magnetic field lines. Okay, so it is because of denseness or closeness of magnetic field lines, because of which this point, that means A produces stronger magnetic field and B produces weaker magnetic field. Remember, same current is flowing through both the system. Okay, so this, my dear students, is magnetic field due to a circular loop. I hope you understood. Okay, I tried my best to make it as easy as possible. Okay, so now we have come to the end of the video, but before I go, I have a small question for you. I want you to try this, okay, and then show me that you are participating and show me that you are learning by commenting the answer in the comment box. So the question for today is, so let this be point P, and then let this be point Q, then so the question is, okay, you have to tell me whether P is north or south, and similarly you have to tell me whether Q is north or south. So the question is, you have to tell me, okay, what P and Q represents. So question, what does P and Q represent? Comment the answer in the comment box. You tell me what pole is this. P is north pole or south pole. Similarly, you have to comment what pole is Q. Q is north pole or south pole. Look at the magnetic field lines and you comment the answer in the comment box. All right, so I'll be looking forward to your answer. Okay, so thank you all my dear students for tuning in. This video must have been longer, but what to do? Okay, can't make it shorter. So but I hope that now you have understood something. Okay, and if you have understood something, that's the sole purpose of this video. So thank you all my dear students for tuning in, and I'll see you again in the next video.